And hello, welcome YouTube. Welcome to this video on turbulence modeling. So in the last video, we compared some of the HVAC, heating, ventilation, and air conditioning simulations compared to LES to experimental data using the dynamic Smart-Gorensky model. We found that to work pretty decently. And of course, we introduced the Richardson number, which is very important for mixed convection. So this actually tells us the ratio of the natural bit to the forced bit, where anything less than Richardson number less than 0.1, you can for the most part ignore the natural convection, and if the Richardson number is more than 0.1 or more than 0.1, you cannot neglect either. And above 10, if the Richardson number is more than 10, mostly it's a natural convection, and you can sort of neglect the forced convection bit. So this is the Richardson number, which is very important, and in this model where whale was tested for mixed convection, Richardson number was 0.048, which is less than 0.1. So for the most part, you can neglect the natural convection bit. But as we will find out shortly, we actually found that the paper actually reported that this natural convection had a very significant effect on Nusselt number. Why is that the case? Because it actually generates more turbulence in the log law layer. So what do I mean? The log law layer, of course, we have actually two log law layers, right? In turbulence mixed convection, we have our standard log law layer, okay, log law of the wall. So this is U plus against ln Y plus, and then of course you have the turbulence bit, which we cannot exactly fit on this graph, but it might more or less take this kind of shape. I don't know how to scale it with the logarithm, and it's very hard to overlay both of them because for different heat fluxes you will have different log law profile. There's a 1 over ln y squared as we saw in our wall function video. Okay, this is the natural, this is the forced. Now, what happens if they go against each other, right? What happens if they go against each other? Alright, so if they go against each other, the velocity profile will be something like that. So okay, if there's a flow, the forced flow upwards, so forced, and then we have the natural. Okay, so what happens here? Over here we have a lot of turbulence, lots of turbulence. Why is there lots of turbulence? Because the shear rates are high shear. You have high shear rate here. High shear rate. What does high shear rates mean? High shear rate means this del U del Y is very, very big, and this tends to generate lots of turbulence. And as you know, the more turbulence you have, the increase you will have a very much higher increase in heat transfer because of the turbulent transport of heat. It will help the help this area have a lot less thermal resistance, and it will thin the boundary layer out. The viscous or conduction sublayer part will be thinner because you actually generate more turbulence near the wall, and this actually you need to have a lot of a finer grid here, okay, as you'll see shortly. But first I want to introduce you to some numbers, important numbers, dimensionless numbers. First we introduce the what do you call this, Reynolds number, the friction Reynolds number, which is based on U tau again instead of U mean. Why do you want to use this? Well, because in mixed convection or in most flows, you would have a very different kind of characteristic velocity. Alright, let's say you have a mixed convection flow, okay, or maybe I always like to orientate it like this. You have a mixed convection flow with G going like this, and you have your forced convection going like this. So which characteristic velocity are you going to use? Are you going to use this one, or there's also a natural convection If this is a hot wall and this is the cold wall, this is the velocity profile. So there's a hot wall, this is a cold wall, and then you'll have some characteristic velocity here, all right, which is the natural convection characteristic velocity. And then you have the forced convection one. So which one are you going to use? Which velocity are you going to use? So to eliminate this dispute, we tend to use U tau or U star, which is the friction velocity. Okay, this is the friction velocity, which is the tau wall over rho. So using this, okay, using this actually kind of eliminates. It eliminates the discrepancy between having to choose between this characteristic velocity for the natural convection or the forced convection. Okay, and there are some other advantages as well. I mean, because you know, turbulence, we are so concerned with the near wall region. Okay, so this actually is a characteristic velocity in the near wall region. Okay, this is a characteristic velocity in the near wall region. So, and we know that has great importance to do with calculating the heat transfer coefficient, and because it's so closely related to wall shear stress. Okay, so closely related to wall shear stress, and wall shear stress is, you know, universal. Okay, and it will tell you how much turbulence you will probably generate. With a higher wall shear stress, you probably have more turbulence. That's the rule of thumb. Okay, and because you can have this near the wall, it's just based on wall properties. You can actually apply this turbulence Reynolds number, or this friction Reynolds number, to almost any flow. So let's say you have flow over a sphere or an airfoil. You can also calculate what the wall shear stress is here. You can have a U tau, which is equals to tau wall over rho. Okay, and you can say this Reynolds number here is maybe what, 180, depending, and you can actually compare this Reynolds number here to this Reynolds number here. If you were to say Reynolds number tau is also equals to 180, what does this two? Can you compare, you know, these two Reynolds number? And the answer now is yes, you can, because it will tell you, you know, what's the rough ratio of, you know, how much friction there is near the wall and how much turbulence there is in the near wall region, right? And how turbulent the flow is in general. Whereas if you, let's say, compare the Reynolds number by doing this, you have RED equals to U infinity D over nu, and then you will have the Reynolds number based on the mean flow, okay, which is U mean D over nu. Okay, how then are you going to compare these two? It's a bit hard to compare these two Reynolds number. Okay, but of course the assumption I make here is that you can pick a very similar characteristic length scale for here and here, then you can sort of compare. Alright, so that's what the usefulness of the friction Reynolds number is. It kind of eliminates some discrepancy in having to choose a velocity scale. You still have to choose a length scale in order to make a proper comparison between this flow and this flow, but having this friction Reynolds number, it helps to eliminate some of these discrepancies. Now for channel flow, which is what the case is here for Ding's paper, the delta, the length scale here, is actually half the channel width. So when you see delta here, and if you see delta here and it's to do with channel flow, delta usually refers to channel width. So I think sometimes I mixed the delta up with the boundary layer thickness, because delta is also used to denote boundary layer thickness. But in this case, this isn't true. This delta refers to the channel width. So you got to be very careful what this delta actually refers to and do some of your homework. Okay, so you see RE tau, it will pop up a lot. And how does it compare to our usual Reynolds number? So our usual Reynolds number in a channel flow will be the mean velocity times the characteristic length scale over viscosity, as usual. kinematic viscosity, and L equals to 2D, D being the half channel width. So L here is actually a full channel width, right? Okay, L is equals to full channel width. So what is channel flow? Channel flow is actually you have flow between two plates, and then you have a flow, right? You have a mean flow here. Okay, you have a mean flow here. Yeah, a mean flow going through this channel, and then you have some parabolic, oh no, not parabolic profile. You have some power law profile here, and it's 3D, right? 3D flow. Okay, a 3D flow. So you have it's actually a 3D version of the 3D version of flat plate flow. Remember, we have a flat plate flow. We have a flat plate flow. Normally that is we simplified to 2D, but real turbulence is actually in 3D. So we have to simulate 3D flow, for example, for LES or DNS, in order to simulate those turbulent structures, which are in actual fact 3D rather than 2D. Okay, so how does this Reynolds number in this channel flow compared to this friction Reynolds number? Okay, so there is a lot of data to compare the Reynolds number tau versus the friction Reynolds number. Okay, and this is actually from one of the papers by Reynolds number DNS. Okay, let me paste this here. This should go into the video description. Okay. Oh, very low. Okay, I haven't added that in yet. Okay, let me add in the... Oh no, it's lagging. Okay. Wrong paper, wrong paper. DNS of... Okay, oops. Let me try getting the right. Okay, low DNS. DNS of turbulent channel flow at very low Reynolds numbers. So he actually provides some DNS data to compare Reynolds number, the mean Reynolds number against the Reynolds, the friction Reynolds number. So it's just to give you an idea of what it's like. Okay, so for channel flow, these are the following data of friction Reynolds number versus the mean Reynolds number, and this one is the one that we are normally used to. This one's the new one. So to compare both of them, they have a linear relationship as should be expected. Then if you put this data in Excel, and just reminder, both of these are DNS data, so they're pretty reliable. Okay, pretty reliable. So we have this straight line relationship. And if you want to actually set the intercept to 0, which it should be, you'll get Reynolds number. In the mean Reynolds number is about 30.5 or 30.4 times the friction Reynolds number. The R square is about 0.9879. That gives you a rough idea of how to estimate RE tau from REM for channel flow. REM is the mean Reynolds number, right? The one we are normally used to. RE tau is the friction one. So this is just to emphasize, how we can compare the friction Reynolds number to the mean Reynolds number, the one that we are normally used to. Okay, so these are for turbulent and laminar regime, at least in this range of Reynolds number, from about slightly less than 1,000, slightly less than 2,000, all the way up to 5,000 something. So this is what to expect. Okay. Right, and again, the good thing about friction Reynolds number is that you can compare this across all kinds of flow geometry, as long as you have a common length scale. Okay, as long as you have a common length scale. Okay, so in my opinion, maybe the boundary layer length scale would be very common among all of them, but it depends. Again, for pipe flows, your whole flow is bounded, so you separate between the near wall region. and the free shear region, so to speak. Anyway, so I'll move on, and we actually compare the Nusselt number in this mixed convection case, and you'll again see a very big discrepancy here. And you actually compare Whale versus DNS. So actually from Ting's paper, I actually wrote down his values into a table. Okay, so again, you will see several cases here: aiding mixed convection and opposing mixed convection. So alright, I will kind of black this out first. I'll kind of black out the other three first. So we just talk about skin friction coefficient first. So DNS and Whale are the ones I want you to focus on now, because we're comparing LES versus, let's say, DNS. These two models, IDDES, these are actually code K omega SST IDDES, and another DDES model, which I will explain in the next few videos, which I want to explain in the next few videos. That's what I want to do. Okay, we'll go through it step by step first, so we just go through both of these first. So skin friction in aiding mixed convection, for DNS it's about this value, 0.0099, and for Whale model we underpredict CF by 4.9%. So you can see it's 0.0990, 0.09941. IDDES, it's better because it's about 1.7%. So this is a very good, very good agreement. If you remember, IDDES, it's the hybrid between RANS and LES. But anyway, this is the Whale, how the Whale model functions. If you were to predict the Nusselt number, opposing mixed convection. Opposing mixed convection, you can see the CF actually changes, the skin friction coefficient actually changes for opposing mixed convection. Obviously, because the flows are kind of opposite each other, right? And this is for low Richardson number, right? Low Richardson number. Richardson number is about 0.048 or 0.0048, somewhere along those lines, which is a very or 0.048, yeah, 0.048 is very low. Most of the flow is actually forced convection. You can see that just with this little bit, the skin friction coefficient actually changes a lot if you were to compare the DNS data. Over here, the Whale model tends to underpredict the opposing mixed convection CF term. However, of course, you have to look at some other factors as well, such as the mesh size. Actually, mesh size plays a lot in the accuracy, of course, but that I will go on to be later. This is actually based on a relatively it's a standard LES mesh, but the thing is that when you have opposing mixed convection, you will have a lot of turbulence in the boundary layer, a lot of extra turbulence, which your normal, if you were to have a forced convection and you have a certain mesh size, right? So if you have to have if you were to do forced convection or aiding mixed convection, okay, where the turbulent flow, the mean flow, and the natural convection is going the same way, you don't generate a lot of extra turbulence, right? So you can use a certain mesh size for a natural turbulent aiding mixed convection. But if you were to use this same mesh size for opposing, okay, turbulent mixed convection, this will not do, right? This will not do, because now if you were to use the same mesh size for opposing turbulence mixed convection, you actually have a lot more turbulence than this mesh can handle. You have more turbulence than this mesh can handle. So you actually have to refine your mesh a lot instead of using the same mesh size for aiding and opposing mixed convection. So over here the agreement is relatively normal, okay, for LES standards within 5%. Okay, if not, hopefully less, but that's going towards the Reynolds average Navier-Stokes level already when you have IDDES here. Okay, so what was done here is that they used the same mesh size for the aiding mixed convection, and they use the same mesh size in the opposing mixed convection. So for opposing mixed convection, the mesh size here is actually 2 cos. That's why you have this big error. This was actually mentioned in the discussion of the paper. Now for Nusselt number, this is very interesting for heat transfer. Of course, you have a 10.8% reduction, or rather not reduction. You have a 10.8% under prediction in the Nusselt number for wheel model. Okay, so it's decent for heat transfer, but again, you have to take note of this error percentage in 12-15%. So far looks like the biggest error is 12.6%. Okay, so for opposing mixed convection, this is aiding mixed convection. Now look at the opposing mixed convection. See how much the Nusselt number changes. Look at this. This is a 7.42, and then for opposing mixed convection, your Nusselt number actually jumps up by about 3 times. 2 to 3 times, just because it's an opposing mixed convection case. So this is a very, very interesting phenomenon you see here. You compare the DNS data for mixed aiding and opposing mixed opposing convection. Okay, a whale model here will tell you, okay, this is about 10% difference for both of them, so roughly there, but not quite there. There are models that actually do better. Okay, but this is what LES can do for you. Even let's say you use the wrong mesh size. So I'll just block these two out. This for future videos. So this was something at L. His data is as such. It gives you about typical ranges over here of his data. So I didn't copy his table. I copied the values and I made my own table. So I mean, his table is more or less formulated like that, but they won't type like that. I typed it out. Okay, so just use his data to reformulate the table here. Okay, so if you want to compare, let's say, to IDDES, which is known to use a Reynolds average Navier-Stokes formulation near the wall, you'll see that for let's say this one, for let's say aiding mixed convection, you see the Reynolds average Navier-Stokes kind of takes over, and you'll see very good prediction in the aiding mixed convection case for the skin friction. For opposing mixed convection, you know there's a lot more turbulence in opposing mixed convection. Okay, you need to refine your mesh there. Likewise for here, there's a big error due to the mesh in according to the paper, but the Nusselt number, again, it changes. It predicts that change fairly well. But for aiding mixed convection, this Reynolds average Navier-Stokes and LES hybrid tends to work well. And in fact, we want to explore some of that in the next few videos. But for now, that's just to say, okay, for near wall, use of these LES, RANS functions tend to work well. Okay, so I'll discuss more of this paper and kind of transition to DES modeling in the next few videos. So the conclusion for LES is this: it can in fact simulate natural convection and mixed convection flows. Preferably, we want to have a dynamically calculated coefficient or transport equation, for example, the K equation, which was shown to be very successful for fire modeling. And of course, it's best if turbulent Prandtl number is calculated dynamically, but you can still get decent results even if it were constant. So for this data set, the turbulent Prandtl number is actually 0.9 fixed throughout the boundary layer and the center. And even then, it can produce this kind of decently agreeing results for these flows in LES or in the LES case where you have the whale model. So you can still get decent results, as you can see here. Okay, so next time we're going to talk about the DDES or DES, detached eddy simulation, which is a one of the most common hybrid models to use. And yeah, thanks for watching. I'll see you guys again. Bye bye.